Hello everyone, my name is Suyash Gupta and today I will be presenting our paper Resilient Concurrent Consensus for High-Throughput Secure Transaction Processing. This work was done with Jelle and Mohammad at Explorer Systems Lab, University of California, Davis. So, system designers for long have dreamt about having a secure, decentralized and democratic system where folks like Alice, Bob and you and I can participate and have equal rights. So, how can we have a system decentralized? Well, one way is by giving everyone the same data, that is, making everyone a replica of each other. And how can we have democracy in such a system? By giving everyone a right to vote, that is, allowing everyone to send a message to decide on the fate of every transaction. A recent solution that combines these properties and adds an element of security is blockchain technology. But what is blockchain? A blockchain is simply a linked list of blocks, where each block includes the hash of previous block, and each block includes a set of client transactions. Now, what are the applications of blockchain? Blockchain is being used in cryptocurrencies like Bitcoin and Ethereum. It is being used in waste management, energy trading, and so on. Now, at the core of any blockchain application is a Byzantine fault-tolerant consensus protocol. Often such protocols have primary backup, where primary tells to run the consensus and everyone follows the consensus. Let me start by giving an example of one of the earliest known practical Byzantine algorithm, that is PBFT. In PBFT, it allows consent among n replicas of which at most f can be Byzantine, where n is greater than or equal to 3f plus 1. So in this very example which we are talking about, here n is equal to 4 and f equal to 1. Basically, we have 4 replicas. Of those 4 replicas, one of them is the primary, and then we have client who will be sending a transaction to the primary. Now let's assume a client sends a transaction to the primary, and what will primary do is that primary will add a sequence number to that transaction, and he will send it as a pre-prepared message to all the replicas. Now, when a replica gets a pre-prepared message from the primary, what will it do? It will say, okay, I will support the transaction which has been sent by the primary, and it does that by sending a prepare message. Now, each replica waits for prepare messages from majority of other replicas. In this case, majority being 2f plus 1 replicas. Now, once a replica gets 2f plus 1 prepare messages, it has a software guarantee that a majority of good replicas also heard about this request from the primary. So what does it do? It goes ahead and sends a commit message to every other replica. Now, again, when a replica gets commit messages from majority of other replicas, that is basically it gets 2f plus 1 commit messages, it has a stronger guarantee this time that a majority of good replicas not only heard about this request, but also prepared this request. So it goes ahead and executes this transaction and replies to the client. So this is how PBFT is able to achieve consensus on an incoming client transaction with all the replicas. PBFT works fine, it's safe and live. But then what is the issue? The problem is all of these protocols are primary backup, where primary is the king. If primary tells everyone to do a transaction, they follow what primary says. But if primary is malicious, then the system halts, and then everyone has to run a protocol to replace the primary. During this whole process, there will be a fall in throughput. So what is the solution? And that is where our proposal comes. We want to give a democratic solution where every replica has the power to be the primary. We want to ensure there is some sort of parallelism where there are multiple parallel instances of any BFT protocol running. And we want decentralization, that they should ensure that it is always a set of ordered client requests. And how do we do that? We propose resilient concurrent consensus. Now, let me explain RCC paradigm. So RCC is basically a meta protocol. And by meta protocol, we mean is that RCC can take as input any existing BFT protocol. For example, PBFT. And what does RCC say is that tell me how many instances do you want to run in parallel? How many replicas do you want to give the power to be primary? And then RCC runs those Z instances in parallel at each replica. And once each replica completes these Z instances, it creates a global order of all these requests. And then it asks every replica to execute these requests in the global order. Let me explain RCC in more detail through this example. In this example, we'll assume there are four replicas. This is the first replica, this is second replica, third and fourth replica. And we'll basically run two parallel instances in each replica, basically Z equal to 2. And we'll again have some clients and we'll ask each client to send the request. And basically what is happening in that, each replica is running two logical parallel instances. And it's because there are two instances, so we need to designate two replicas as the primary. So we'll call this replica as the primary for the first instance, this replica as the primary for the second instance. And now when these replicas get client request, now they'll start running the PBFT protocol among their own logical instances. So now in this case, the client is sending the transaction. And when this happens, each of the primary will send a prepare message to their own logical instance, which are basically the replicas. And then the same phases of PBFT happen. Next, the prepare phase, every primary assigns sequence number, and then every replica supports through prepare message. And then the commit phase, where then every replica try to again send a commit message. Now at this point in time, each replica has got commit messages for both the requests. And when that happens, they go ahead and execute the transaction and reply to the client. So this is how RCC is working. Now, everything looks nice, but what are the challenges in RCC's design? Well, any protocol that allows multiple replicas to act as the primary has interesting new challenges. For example, how to securely order the transactions. Or is it possible that failure of one instance cause other instances to stop? Or how can we ensure that there's always a continuous ordering request? Finally, because this protocol allows multiple replicas to be primary, can there be coordinated attacks? So let me explain some of these challenges. The first challenge we'll see is secure ordering. We want to see why does it matter? Why do we need to have ordering of all the requests securely? For that, we'll take a simple smart contract, which basically transfer A, B, M. If balance of A is greater than M, then we add M to the B's balance and subtract M from A's balance. And we'll have three of our players, which are Alice, Bob, and Eve. Initially, they start with a balance of 500. And we'll have two transactions, T1 and T2, where T1 basically what it does is that takes $2 from Alice's account and puts to Bob's account. And then takes T2, what it does is that it takes $1 from Bob's account and puts into Eve's account. And what we are trying to show is that the order in which these transactions are arranged or they're executed can basically give benefit to some players. For example, if I do T1 first and then T2, then what will happen after doing T1 is that Alice's balance changes to 3 and Bob gets $2 in his account. And then when I run T2, Bob will have $1 and Eve will have $1. But now, if I do something different, if I do T2 followed by T1, then by doing T2, nothing changes because Bob has $0 in his account. But then I do run T1, then Bob gets $2 in the account. So it will be beneficial for the Bob if somehow the order is T2 followed by T1. So in such multiple primary protocols, what we need is an ordering which is secure so that replicas or clients are not able to change it ahead of time. Another challenge that we want to see is that can malicious replicas collide together? Basically, we have multiple primaries, and can these primaries work together to ensure the system is not performing well? Well, we'll assume a scenario where we have our two F+1 replicas divided into three sets, A, B, and C, each having A and B having F replicas, C having one replica, and rest of the malicious replicas are here in set M. And we have two primaries, and both of the primaries are malicious P1 and P2. And now what we see is that P1 sends the transaction T1 to replicas in A and C and to all the malicious replica. And P2 sends transaction replicas in B and C into all the malicious replica. Note that P1 did not send T1 to replicas in B, and P2 did not send T2 to replicas in A. So replicas in M can execute both a transaction, replica in C can do it, they both reply to the client, but replicas in A and B are stuck. They cannot do any progress because they don't have either of the transactions. And replicas in A can complain, hey, P2 is malicious, but nobody will believe them because there are only F of them. And similarly, replicas in B can say that P1 is malicious, but nobody will believe them because there are only F of them. So what is the solution in this scenario? The whole system is stuck. And we need to find such solutions for a multi-primary protocol. The key ingredient of RC is that there are always good instances that are live. In specific, if there's an instance that has failed, then we do not replace it, we only stop it, and we let its consensus complete through an independent instance. Further, if in future these failed instances against are working good, we allow them to be restarted. Also, as we showed in the previous slide, that there is a possibility of collusion attacks. Then how should we detect them? Well, to detect them, what we do is that we say that if there are at least F+1 replicas who are blaming multiple primaries, then we know there is a collusion attack. And a solution to resolve this collusion attack is to basically send lightweight checkpoints. These checkpoints bring all the replicas back to the same state and allow the system to progress. So where did we actually implement RCC? We implemented RCC on ResilientDB, which is a high throughput yielding scalable permission fabric. ResilientDB is open source and can be downloaded, and it was presented at ICDE and VLDB. So why ResilientDB? Because ResilientDB provides a multi-threaded deep pipeline architecture with each replica. In specific, if we look each replica as a black box implemented on ResilientDB, then there's a network through which all the messages come. And then ResilientDB provides a lot of threads to parallelize the task of a consensus. For example, any incoming messages from the network are handled by input threads. If there are client requests, then they'll be handled by batching threads. If there are prepare incoming messages, then they will be handled by worker threads. And it is possible some messages need to be sent to the network, so we have output thread for doing that. And some messages need to be executed. For that, we have execution thread. Now, let's try to see some results of evaluating RCC on ResilientDB. So here are the metrics of our system and what we deployed up to 320,000 clients, and we had 16 core machines. And we ran experiments 180 seconds, of which first 60 seconds were used for warm. So as I said, the RCC can have Z instances, so we wanted to play with different values of Z. We played with RCC having only 3 primaries, having F+1 primaries, and having N primaries. And we compared against 4 state-of-the protocols like PBFT, ZZWAS, SBMT, and hot stuff. And what we saw is that all the variations of RCC were scaling much better than all other protocols. And they were getting less latency. So we thought of seeing maybe batching helps this protocol, maybe by increasing the batch size, these protocols can start performing well. And even in those cases, we saw that RCC variants were outperforming existing protocols. So to conclude, RCC is a meta BFT protocol that delegates power to each replica. It allows every replica to be the primary. It allows running parallel consensus. RCC guarantees that there will be always a set of ordered client requests. RCC provides solution that can handle collusion attacks because it is a multi-primary protocol, so multiple replicas can collude together. And RCC ensures that there's a secure ordering of requests. There will always be a good request being ordered. Thank you.